Okay, so we've just gotten our definitions for limits at infinity and the definition of a horizontal asymptote here. And now we're wondering, okay, how are we actually going to find limits that look like this? Um, Remember our limit tricks from a previous section, 2.2, part 2, I believe? Um, in there, we had things like direct substitution, factoring and canceling, stuff like that. Um, Notice that with these, direct substitution is so not a trick that we can use on this. You cannot plug in infinity because it's not actually a number. So make sure you don't fall into that trap. Sometimes it can be a little tempting to try and plug in infinity. I'm making little quotes with my fingers right now, so imagine that. But you can't plug in infinity. It doesn't work that way. So we've got to come up with some other tricks to use. And the main thing that we're going to employ here is a very, very useful theorem and an extension to that theorem that's going to really help us find these limits. And the theorem involves some limits itself. Here it is. It says that the limit as x approaches infinity of 1 over x to the r equals 0. Okay, so that is the theorem statement. And r here is any rational number. So any whole number or fraction, anything that can be written in rational form. Okay, so this limit is 0. Now, if you think about why that is, okay, we are taking x to some power. Okay, and then that is in the denominator of a fraction. So imagine, if you will, values of x that are getting very large. So think of a large number right now, like a really large number. For me, I think I'll pick a billion. Okay, one with 9 zeros after it. So 1 over my number, 1 billion, 1 billion. Okay, that is a very, very tiny number when we do 1 over 1 billion there. That would be 0.000000000. How many zeros is that? 0, 1, something along those lines. Anyway, it's a very, very small value. And that's just with 1 billion to the first power. Imagine if that was some other rational number, like, let's see, you know, whole numbers count as rational numbers. What if I said that was to the fourth? Okay, that would then be even tinier because the denominator is getting so huge. Okay, 1 over a huge value is going to give you something very, very small. Okay, huge denominator equals tiny, tiny value. Okay, so as x approaches infinity, that's numbers that are even larger than a billion, okay? So you can imagine that denominator is going to get just simply massive, leaving us with very, very, very tiny numbers. As x goes to infinity, we say that value gets so small that we can consider it 0, okay? So our limit for the values is 0. Now the same thing's going to happen if you do this in the negative direction. Limit as x approaches negative infinity of, 1 over x to the r power. That also equals 0 because, again, you're going to be getting a huge denominator here. All right, 1 over that massive number is going to be so small as x gets close to negative infinity. it's going to be a negative number, but it's going to be such a tiny result that we say the limit is approaching 0. Okay, so that is the useful theorem here. Now the extension to this is just replacing that 1 on top. So we can say that the limit as x approaches infinity of any constant over x to the r is going to equal 0. So k is any constant here. All right, and you can picture this either kind of like how we were doing this useful theorem. K is just some constant. It could be even a fairly large constant, like maybe even 1,000 or 1,000,000 itself. But infinity is so much larger. As x approaches infinity, this denominator is just going to grow without bound, we would say. So that denominator, once again, is just so huge that the limit of any constant over that huge denominator is going to be approaching 0. Okay. So we can say that for any constant. This also works for x approaching negative infinity. We can write that in as well. Limit as x approaches negative infinity, k over x to the r, that's also going to equal 0. You could also calculate these extensions by using one of the limit laws, by the way. I'll kind of write that off to the side somewhere here. Limit law. We're just multiplying a constant, k, times the function 1 over x to the r. And so the limit laws say that if you multiply a constant times your function, to take the limit of that, you can just multiply the constant times the limit of the original function. So this is like a constant times limit of 1 over x to the r as x goes to infinity. That would be 0 according to our theorem. So you'd have k times 0, which still gives you a limit of 0. Okay, so that's 2 ways of thinking about the extension there. Use whichever one makes the most sense to you. Just kind of remember for the overall idea here, as the denominator of these functions gets very large, the result is so small, and the limit of that we say goes to 0.